I should say that, as you know, we got the blue screen of death at the beginning of class last time, and that never happened on my laptop before. And at the beginning of the first section that I teach before you, I got the blue screen of death again. So I am a little anxious that something with all of these different programs open and Zoom and the webcam, if it happens again, just be patient. But if it becomes a frequent occurrence, I'll either figure it out or get a new machine. My machine's pretty old. Anyway, so we'll come back to this question a little bit later on in the lecture. Let's do some announcement type things. First of all, we're going to have a little pitch here. Now, normally I don't, when I'm in a classroom setting, being a large class, a large lecture, most student organizations approach you wanting to take the first few minutes of your class to inform you about a student organization or an opportunity or a program. And usually I turn those down because they really eat into class time and they're not germane to the topic, with the exception of a few of the clubs on campus that are connected to physics and astronomy. And so we're going to hear about two of these organizations briefly. Isabel, yep, there you are, Isabel. So I'm going to turn it over to you, and I think screen share is still connected. So you should be able to take over and tell everyone about these opportunities, and then I'll continue with the lecture after that.
Great, thank you so much. I'm going to go ahead and share my screen. So hi everyone, my name is Izzy Ford. My pronouns are she, her, and I'm here to talk to you today about two really great clubs that you can get involved in if you're a physics major, minor, if you're really interested in astronomy, you're thinking about pursuing either of those, or even if you're in a related STEM major and you have to go through any physics classes in your time at UNC, these are really great organizations to join. So the first one I'm going to talk to you about is Visibility in Physics. And what we do in Visibility in Physics is create an encouraging social atmosphere for underrepresented minorities and allies in physics. We host events such like faculty dinners. We do how to get involved in research. We talk about how to write a research poster. We hosted a career fair last year and we'll be hosting a career panel this year. And we also talk about things like imposter syndrome, what to do when you feel like you're not good enough, things like that. So if you're interested in joining any of those meetings, you can join you can join our listserv at the bottom of the screen, and our interest meeting will be Wednesday, August 26th at 6:30 p.m. via the Zoom link on the screen. You have to use your UNC email to join the Zoom, is the only thing I will note. The second club I want to talk to you about is Society of Physics Students, and we're really focused on creating a community that encourages collaboration within physics. We host things, we do a lot of graduate student research talks, we have professors come in and talk about their research, undergrads will come in and give research chalk talks. We also do social things like game nights, we do resume workshops, things like that. So if that's interesting to you, yeah, interest meeting for SPS will be Thursday, August 27th at 7 p.m. via the Zoom link there. And you can sign up using the same link to sign up for either one of the listservs that I've mentioned today. And then one quick note on something we're piloting in SPS this semester is the Physics Foundation seminars. These seminars are going to be student-led seminars to kind of reinforce any knowledge gaps that you may encounter in your time in physics classes. So if you have to take maybe Physics 114 or 115 or even 118 or 119, you need to know a lot of calculus for those classes and a lot of math, some trigonometry, stuff that you may not remember from when you took the class originally. So these seminars are designed to kind of help you remember those concepts and get more practice with them so that you can really succeed within your classes. If you're interested in getting those emails about when the seminars will be, go ahead and sign up for the SPS listserv. And thank you so much for letting me steal a bit of your time. I'll put my email in the chat. Please feel free to reach out to me if you have any questions, comments, concerns.
All right. Thank you very much. Of course, this is a big survey class, and I know you're not all going to become physicists and astronomers, but usually we have a fair fraction of people who are interested in this, or at least thinking about the possibility of this. And these two student organizations have been very active and a good way to form student community in these areas. So I highly recommend them. Okay, let me share my screen again. Slide everyone back over here. Okay, so let's see. Last time we had finished, or mostly finished, our discussion of size and scale. Oh, I should pause and ask if there are any, important questions. They want anything having to do with the syllabus or anything anyone needs to know right up front. If not, there'll be time on the tail end for such things. Okay, and of course you can interrupt me at any point. Please do so with questions as I'm going through the material. Okay, so we had mostly wrapped up size and scale. Now, there's one more thing I'd like you to take a look at. And let me go to the ebook. So this is under lesson 1, and come down to size and scale. Slide on down and you can see the exercises. Now, I'm going to warn you, for most of these sections and subsections, a lot of these links are broken. A lot of these are apps that were put together by University of Nebraska-Lincoln that were pretty good to help convey some of the concepts that we teach in class. And so I put a bunch of them in here, but they were Flash-based and they're just not available anymore, and the links haven't been removed yet, and I haven't found substitutes. So if you click on a link down under the exercises and it doesn't work, don't panic or anything, it's not a big deal. Now, some of the exercises are things I really do want you to try, and I will point those out. For example, I did mention Google Earth. That might be a good one to try. I think this Powers of 10 video with Morgan Freeman is no longer available because of copyright issues. It was taken from some History Channel or Science Channel program. It was quite good, and maybe I'll try to find it and relink it. But this last one here is actually really good, and so I brought it up in the screen over here. I figured maybe I'll spend a minute going through it. I wasn't going to, but in the first class, since I got the blue screen of death and lost some time, and assuming we don't get the blue screen of death this section, that means we have some extra time because I want to keep the two in sync. So maybe I'll walk through it with you. And let me start it up here. And when you start it, it has this really soothing, trippy, celestial music. I'm going to turn that off. And what this does, there's a slider here that lets you slide up to the largest scales imaginable and the smallest scales imaginable. And I should say this is Flash-based, so it won't work for all of you. If you do have Flash on your computer, you can play with it. If not, let's just take a look right now. And here we have the 1 meter scale. As I slide this and go out to larger and larger scales, then we'll see it goes by factors of 1,000. We'll see 1 meter, 1,000 meters, and so forth and so on, with representative objects at each scale. So again, one way to figure out our sense of how big the universe is how big is something compared to something else that we may already understand. So here we are at human scales. You have different things there. Yeah, I'll zoom out first. Giant earthworm. I had no idea they got that big. Elephants, dinosaurs, giraffes. There's the lunar lander. Some rather large dinosaurs. Blue whale. There's a Boeing 747. Statue of Liberty, a football field. Titanic, some famous monuments. And there we are at the 1,000 meter scale. I'll keep going on out. World's tallest building, or one of them. Vatican City, Angel Falls. Now we have an asteroid there as well, one of the smaller ones. There's Mount Everest. The Large Hadron Collider is a particle accelerator. Phobos and Deimos are the moons of Mars. Neutron star is a type of dead star. There's Rhode Island. Some of the moons of Pluto. States and countries, the Grand Canyon. Larger states, larger countries. There we have some dwarf planets. Moons, major moons in the solar system. There's Mercury, Mars, so now planets as well. Sirius B is another type of dead star called a white dwarf. Here's the Minecraft world to give it a sense of scale. There's Jupiter, and then some of the smallest stars are not much bigger than gas giants. We call these red dwarfs. Now we're getting out into scales that we cover in Astro 102, but still it's fun to think about here. Larger and larger stars, you can see there's a wide range of stellar sizes. Getting into giants and supergiants. There's Betelgeuse, which we'll come across again today. There's our whole solar system and the distance that the Voyager 1 spacecraft has traveled. Distance to a comet. You also saw a light day there, how long it takes light to travel, or how far it travels in one day. Then some nebulae. These are planetary nebulae, something that happens near the end of a star's lifetime. They throw off some of their outer layers, making these pretty nebulae. Horsehead Nebula is a famous one. Pillars of Creation is another famous one. The Crab Nebula, the Orion Nebula, Eagle. So some of these you may be familiar with. Then we're getting into like Tarantula Nebula there. These are large star-forming regions, and then small dwarfish galaxies, represented with those star clusters there, not actual pictures in this case. Dwarf galaxies, the Magellanic Clouds, which orbit our galaxy. There's our galaxy, the Milky Way. Let me move my mouse here. I've run out of space on my mouse pad. Distance to Andromeda. There's our local grouping of galaxies, local cluster of galaxies. Superclusters. Then we're getting out to the scale of large-scale structure, distance to the Hubble Deep Field, and the entire observable universe. So I think that's a great way for getting the sense of scale of things. We can slide back down. Although we won't do as much of the small stuff in this course, we will dabble on small stuff on occasion. So maybe we'll go in the other direction because it's fun. So let's see, we're back up here to human scales. We have a basketball, that's appropriate for us. Approximate size of this viewport. Small animals, matchstick, coffee bean, ant, bacteria, dust mites, width of a human hair, skin cells, blood cells, chromosomes. We're seeing different types of light as well, with smaller and smaller wavelengths as we go. Viruses, DNA strand, getting down to complex molecules and now to simple molecules. This one right here is kind of nifty. Smallest thing you can see in an electron microscope is that gray region. Simple atoms. Then we get to subatomic scales, and there's not much. Each circle is a factor of 1,000. Then we get down to the nuclei of atoms. Complex ones, simple ones. We can keep going. Lengths shorter than this are not confirmed, not experimentally anyway. And then these are quarks. Protons and neutrons are made of smaller things called quarks. Other small little particles, neutrinos. And then it's a bunch of nothing and nothing until you get down to the very fabric of space and time itself. And these, of course, are kind of theoretical, whether particles exist as strings and whether, what space and time look like on the smallest scales. Is it fuzzy and quantum mechanic-y? Anyway, we'll talk about some of those topics in this course as well. Anyway, it's fun to play with, and hopefully that also gives you a sense for the vast scales that we talk about in astronomy classes. Questions about any of that? Okay, Well, let's move on to our next topic. Let's see, I'll actually keep that window up and just bring this. Doc cam. Okay, so our next topic after size and scale will be constellations and the celestial sphere. So if you've read ahead in the textbook, you have some familiarity with these concepts. Get this up well already, which is always good. So constellations and the celestial sphere. How many of you who out there took this course because you wanted to learn the constellations? 1, 2, 3, 4, lots of you. Sucks to be all of you then, because I only know 6 or 7 constellations. And I'm a practicing, professional astronomer. So that means that nowadays professional astronomers don't need to actually know the constellations to do their work. And we'll get into the reason as to why that is. We will talk about some constellations, but we're not going to go through all of them. It's not the focus of this course. And so let's talk about the reasons why. Now, back in the day, long time ago, professional astronomers did need to know the constellations. They were very useful, very practical. And they also served other practical purposes. So anyone want to venture some guesses? What are some of the practical uses of constellations for astronomers and for others?
Navigation.
Navigation's the big one. So if you're out on the open seas and can't see land or anything, it's just the water and the stars, you can use the stars to get your bearings. If you know the constellations, you can find the one that includes Polaris, the North Star, which is always due north or very, very close to due north. So that way you know where north is, and hence you know south and east and west. So that's very useful. Also, if you know the constellations, where they appear in the sky, if you have some kind of clock on board, and this was actually one of the things that slowed down the initial exploration of the globe by ship. We need to invent really good clocks. Once we had those clocks, you can pair that with information you see in the sky to know where you are, how far east and how far west. So navigation is a good example, but the captain, the first mate, and other people knew how to do this. You didn't take a professional astronomer along with you on your sea voyage. So what are some other applications of knowing the constellations?
They can tell you what season it is.
Season, yes. And we'll see this particularly at the beginning of lesson 2, all the way back to prehistory, going to archaeological sites. You can find a lot of astronomy built in. They built very simple calendars marking where the sun rises on the horizon or sets on the horizon for different times of year. And this would let them know where they are in the calendar. And this is really important in agrarian societies for planting crops. If you plant too early or too late, more people than usual die that year. And so it's really critical to get the timing of that correct. But again, this is just stuff people figured out. Back then, everyone knew what the sky looked like, how it moved, how it worked. Nowadays, we have to have college classes for this because no one looks up anymore. But back then, when it was, primarily an agricultural, most civilizations were agricultural, you get up before the sun, you go to sleep when the sun goes down, but you knew the stars and you knew how it worked. There's nothing else to do, really. There's no internet, no TV. The sky was at least one form of entertainment. Everyone knew how all this stuff worked. And so they figured out very quickly you can use it as a calendar. But still, you don't need a professional astronomer for that because everyone knew how to do it. So what about professional astronomers? Why would they need to know the constellations back then, but not now?
If something funky was going on with one of the stars, they would need to know what constellation it was in to tell the other astronomers what to look for.
Precisely, exactly. So let's pull up a constellation here. This is where I go back to, here we go. So here's a constellation. What constellation is this? Anyone know?
Orion.
Orion. Yep, it's constellation Orion. So let's say something funky is going on with one of the stars. Let's say I'm observing And I noticed one of these stars is getting brighter and fainter and brighter and fainter, and it normally doesn't do this. So that's something I want to convey to my colleagues so they can study it as well, confirming my observations or monitoring it when I can't, because maybe it's daytime where I'm at, or maybe I'm clouded out. And it's actually, this is a germane example because the star Betelgeuse, that's this bright red star right here, just this year was fading and fading and fading. It varies in brightness, but it got really faint, unusually faint, fainter than any time in the historical record. It was about as bright as maybe this star over here. So very noticeable, but it has since re-brightened. Some people were thinking maybe it would be a supernova explosion, something you only see every couple hundred years, and we're getting excited, but no, it was just doing something strange, and it's back to normal now. Anyway, let me pick one, maybe this one right here. So I would tell other astronomers, okay, look at the constellation Orion, go to its belt, and jump off the top star in the belt and move towards Rigel, which is the big blue star in the foot of Orion the Hunter. Maybe go 1/3 the way to Rigel from this top star in the belt. So, I gave instructions on how to bounce around and find this particular star, and then they can do their studies. So it's useful for that reason. Now, nowadays, we don't do it that way. Instead of giving that complicated sequence of instructions, what would I just give them?
Give them the celestial coordinates, probably.
Celestial coordinates, that's right. We have a coordinate system for the sky. It's kind of like the coordinate system we have here on Earth, like your GPS. Your GPS can tell you where you are on Earth, and it can give you that information Earth's coordinate system is longitude and latitude. Earth is this two-dimensional, the surface of Earth is this two-dimensional surface, curved surface, spherical surface, and so it only takes two coordinates. And what do we call those coordinates on the Earth?
Longitude and latitude?
Longitude and latitude. And so we can do the same thing for the sky. We don't call them longitude and latitude, we call them something different. I'll write that down in a second, but it's a similar idea. Imagine taking the longitude and latitude coordinate system, here it is on Earth, and projecting it outward to the sky, and then connecting to the sky. And so you can have a coordinate system on the sky. Now, the only reason this works is because we can't really see distance. Like when you go out at night and look up at the sky, can you tell how far away the stars are just by looking at them? No, you can't. Some may be brighter and fainter, and you may think the bright ones are closer and the faint ones are farther. That's usually not the case either. The bright ones are usually just much more luminous, cranking out a lot more light. So the brightness of the star doesn't really tell you the distance. You look up and it just looks like they're all kind of at a common distance, almost as if there is a sphere, a real sphere encompassing us with the stars attached to that sphere or painted onto that sphere. And back in the day, that's what the ancients believed. They believed Earth was the center of all things, kind of like in this slide that I'm showing, and that there was a real transparent crystalline sphere surrounding us, and the stars were attached to it. And nowadays we know that space, it's three-dimensional. The objects are distributed through three-dimensional space, and they sit there, and we rotate on our axis. But back then, they thought Earth was stationary, and the entire universe, which to them is this sphere, is rotating around us. And particularly as we get into lesson 2, we'll talk about these ancient models of the universe and how they transitioned into the models that we have today. Anyway, let me see what's coming up next. I should also say that this is why a planetarium works. When you go into a planetarium chamber and they project the sky up onto the dome, the projector's at the center, and on that dome, all the projected stars are the same distance from that projector, yet it looks like the real sky, because again, we don't have a good comprehension, a good understanding of distance. We can't just see it. There are ways we can measure distances. It's tricky. It's a bag of tricks for figuring out things farther and farther and farther out. And the lab course is kind of designed around this bag of tricks. called the cosmic distance ladder. And we'll touch on some of those in this class as well. Anyway, let's write down what these coordinate systems are called. I'll put up the dot cam. And so in the case of Earth, as you told me, we're talking about longitude and latitude. And which one, let's see, I have a globe here. Which one is changing its value as you go from the North Pole all the way down to the South Pole? Which one changes in value?
Latitude.
Latitude.
Latitude, that's right. Latitude is changing as you go this way. That's also called a line of constant longitude. Longitude goes around the belly. So if you pick one longitude and hold steady at that longitude, you have a line of constant longitude. It's a line of changing latitude. Often people get confused between the two, so I often put the extra word in there, constant or changing. In the case of latitude, we're running from minus 90 degrees all the way out to plus 90 degrees. And longitude, that's going around the belly of the Earth, and that's a full circle, 360 degrees in a circle. So this goes from 0 degrees to 360 degrees. And you have to pick some point to be 0. It's a loop. It keeps going around and around. And so it's kind of an arbitrary decision made a long time ago. Greenwich Observatory in England used to be the world's best observatory, and they declared themselves to be longitude 0. And so that convention has stuck. Now in the sky, they have different names. Instead of longitude, it's called right ascension. Instead of latitude, it's called declination. But they're the same ranges, minus 90 degrees to plus 90, longitude 0 to 360 degrees. Now, with one little exception, here we have the celestial sphere, and you can see this is plus 90 deck with declination, plus 60 deck, plus 30 deck. 0 declination is the celestial equator. That's just Earth's equator projected out onto the sky, minus 30, minus 60, minus 90. But in terms of right ascension, you can see they're not marked in degrees, but hours. Here's 4, 6, 8, 10, 12. And the reason for that, you can do either degrees or hours, but astronomers tend to use hours because this sphere goes around once a day, once every 24 hours. So if the star is over top of you, maybe we call that it's right ascension 1 hour. Then an hour later, stars at 2 hours right ascension will be overhead. An hour later, stars at 3 hours right ascension will be overhead, and so forth and so on. So since the whole thing spins once a day, we can measure it in hours or degrees, and both are used by astronomers. Okay.
What are they called again?
What is what?
What are they called again? The space version of latitude and longitude?
I'm sorry. I wrote it down, but I probably didn't have the dot cam up when I did it. So here it is: sky, right ascension is the equivalent of longitude, declination is the equivalent of latitude. The only difference is they don't rotate together. One is fixed to the Earth, one is fixed to the celestial sphere, this idea of a sphere around us. You know, in ancient days, they thought Earth was stationary and the sphere was moving. Nowadays, we realize that space is stationary, so the celestial coordinates are stationary, and Earth is rotating underneath. Okay, let's get back to constellations just for a little bit, and then we'll talk about the motion of the celestial sphere. So constellations, and why we're really not going to get too far into them in this course. Like again, here's Orion, the hunter, but it's really just a collection of stars, a random smattering of stars on the sky. And Western Hemisphere looked at this collection of stars and saw the pattern of, well, I guess some guy beating a dead animal, apparently, the hunter Orion. But that's Western civilization. Other civilizations looked at the same pattern of stars and connected the dots differently. Often they drew pictures of people or faces because the human brain is actually wired to find faces in particular, people, but faces in particular in random patterns. I don't know if you've ever experienced this. If you've looked at like random patterns in tile or a carpet or the ceiling and see faces, or maybe it's just my own personal psychological problem. But no, this is a verified phenomena. The human brain is wired to identify faces from birth, because it's helpful to know who your mom is and stuff like that shortly after you're born. Another example of that is the moon. Have you seen the face in the moon? Yeah, okay. Now, an interesting thing about that, the moon and also the constellation Orion, I'll give you a personal example. I got on a plane in Miami and flew to my telescopes in Chile some time ago. It was a nighttime flight, and outside the window I saw the constellation Orion. And so it started looking like this, but by the time I got to Chile, what was the configuration? How was it different? It was upside down. Yep. It didn't really change. I changed. I started by standing up like this. By the time I got to Chile, I was upside down. So from my point of view, the constellation has changed. And people in the southern hemisphere are not going to imagine a hunter standing on its head, or upside down people, or upside down anything. So they're going to connect the dots differently, and they're going to incorporate their culture and their stories when they do so. So all different cultures have different ways of connecting the dots. Just Western civilization's way of doing it has become the sort of official version. Another reason why this is more a subject for an anthropology course than a science course is if we got off the Earth and went off in space and looked at this constellation from the side, yeah, we like to think of them, all those points of light, as being at a common distance because we can't see distance. But they're really at different distances. So if we view it from some other angle, like thousands of light years out, and looking at it, it doesn't look like a hunter at all. All these stars are, I don't know what that would look like as viewed from this direction. So it's really an Earth-centric anthropological concept. Also, the stars move with time. Over the course of thousands of years, gravitationally, they pull and tug towards each other, which distorts the shapes in the sky, distorts the constellations. Okay, for all those reasons, we're not going to get into the constellations in any great depth. Also, with the moon there, when you're in the southern hemisphere with the moon, it's upside down. And you may not realize it, and it looks it's disconcerting. You look at it and something's not right. You don't see a face in the moon when you're in the southern hemisphere. When we talk about the face in the moon, people in the southern hemisphere really don't know what we're talking about, because again, they're seeing it from a different perspective. Anyway, I will throw a few constellations up from time to time when it's relevant, but we're not going to spend a lot of time learning Western civilization's version of connect the dots as you like. Okay, let me see what's next. Okay, so next I want to talk about, let's go back to the celestial sphere. I want to talk about how the celestial sphere moves. And let me see, I got about 15 minutes. Let's see how far I can get. So this is a piece of the sky. And when I'm teaching in a classroom, I put it up on the big screens. I normally have 2 screens, and I tell the students to imagine it just filling the classroom, like you're in a planetarium chamber. This is trickier because we're all in different rooms and we're just looking at computer screens. But just imagine this little patch of the sky continuing off the left and right of your computer screen, off the top and the bottom, and wrapping around you. So you're in this celestial sphere. And the question is, which way is this patch going to move? And to do that, we have to orient ourselves. Again, this is tricky. Normally, we would all be in the same classroom. Instead, we're all in different rooms with different orientations. So while in astronomy class, we're going to just adopt something that's not necessarily true for where you happen to be sitting at the moment. But in my classroom that I normally teach, north is this way. Try to line it up with the camera there. Yeah, north is this way. It means south is that way. So which way is east? Is it behind you, or is it towards your computer? If we pretend, all of you pretend, for this class, north is that way. Where's east? It's behind you. That's right. So that will be the official coordinate system of our virtual classroom. And that means these stars that you're looking at are in the west. Now, given that they're in the west, probably close to the horizon, where are they going? Are they rising up off the top of your screen, or are they setting? Do you know which way the stars go? So going up or down, you have a 50-50 chance. Be bold.
I'm gonna vote up.
Going down.
Down.
I'll say down.
Okay, I think we have a down majority, and down is correct. The stars rise in the east and set in the west. So they're coming up behind you and setting down in front of you. Now, again, this is just our perception. The universe is not spinning around us. The ancients thought that because they thought we were that special, but we're not. It's just there and we're spinning. So if the sky appears to be spinning east to west, that means Earth is going in what direction? What to what? Go ahead, chat it out. The sky's going east to west. That means Earth is in reality spinning underneath it. What?
West to east.
West to east, opposite.
Yep, opposite. So let me grab my globe again here. Get the United States in your field of view. West to east. That means Earth is spinning this way. So let me do that. My globe's a little squeaky. Sorry about that. Is that clockwise or counterclockwise?
Counterclockwise.
Counterclockwise.
Hey, whoop, damn it. Keep it up and spin here. Okay, clockwise or counterclockwise?
Clockwise.
Clockwise. So the direction of spin really depends on how you're viewing it. The convention is being above looking down. If we went up to the North Pole, jumped off and looked down, it would be counterclockwise. So we refer to Earth's motion as a counterclockwise rotation. Most things in the solar system are also counterclockwise. Again, if you went up off the top of the Earth, up, turned around, looked down on the solar system, most things would be spinning counterclockwise. They'd be orbiting counterclockwise, both planets around the sun and moons around planets. A few exceptions, and we'll learn why. But just remember, it depends on your point of view. Okay, so that's how Earth is spinning. Let's throw the celestial sphere in here as well. For that, I've set my little office up here to, let me get the doc cam up. And I've set up a demo table. And now I just got to flip it. There we go. Okay, pretty good. And I'm going to go over there. I can't see you all, but you should still be able to hear me. So we have the Earth here. And I'll put it down on the table. You can think of the table as the plane of the solar system. I'll step back so my head's not cut off. Plane of the solar system. So if we extend the table far enough out, we run into other planets and the sun and whatnot. And here's Earth's position in the solar system. And you can see its rotation axis. It's tipped a little bit. This is because early in our history, as we'll learn, we were hit by another planet essentially. It tipped us over, helped to form the moon. And we're going west to east. And the celestial sphere is above us. Again, it's really just a mental construct. Things are not painted to this sphere. And an umbrella makes for a good celestial sphere. You even have the right ascension declination coordinate system built into it. As I go down these rungs, I'm going from deck of plus 90 down to lower declinations. As I go from rung to rung to rung, I'm changing the right ascension. So it's a partial celestial sphere. You'll have to imagine the rest of it. And the way it works is you just continue Earth's rotation axis out through the shaft of the umbrella here, the celestial sphere. The Earth is, in reality, space is just sitting there and Earth is spinning underneath it. But from our point of view, we're stationary, which means the sky is rotating the other way, things rising in the east, setting in the west. So from our point of view, this is how the sky works. It's rotating around us, but I'll just flip it over here for a little bit. And the question is there a point where the stars will not appear to move?
The middle of the umbrella.
Yeah, the middle of the umbrella. And actually, is it one point? It's 2 points. Just imagine the sphere coming down around and extending the shaft down below. There'll be another point as well. So 2 points in the sky where the stars are stationary. And we call these the celestial poles. And let me write that down. Okay, that worked adequately, I think. Get back to the doc cam and flip it around. Okay, so we call these the celestial poles. North celestial pole, south celestial pole. If we say North Pole, we're referring to on Earth, like where Santa lives. North celestial pole is on the celestial sphere. Okay, let me see what's next. So at very close to the north celestial pole, let me see if that's what's next. We have a bright star. What do we call that bright star?
Polaris.
Polaris.
Polaris, that's right. And this is just an aside, but if you're trying to find Polaris in the sky, it can be a little tricky. But again, this is the star the navigators, at least in the northern hemisphere, were looking for. In the southern hemisphere, there's no bright star at the south celestial pole. So navigating in the southern hemisphere was a little trickier. But in the northern hemisphere, you'd want to find it. And here we have two constellations. This is the Big Dipper and the Little Dipper. And the stars in the Big Dipper are pretty bright. So even under, being in a city where the city lights make it harder to see the stars, you can still pick out the Big Dipper. And so find the Big Dipper and then find the last two stars in the Dipper here and just continue on a line, I don't know, 30, 40 degrees out, something like that. And you'll come across this star here, and that's Polaris. The last star in the Little Dipper is Polaris. Now these other stars, you'll see a couple of them, but most are too faint to see under city conditions. But of course, if you're at a dark site, you can see all of them quite easily. Anyway, that is Polaris. So let me ask you some questions. If we were at the North Pole of Earth, where would Polaris be? Where would the North Celestial Pole be? Point to it. That's right, it'd be directly overhead, and that is something we call zenith. Let me write that down here. Zenith is overhead. No matter where you are on the planet, overhead, we call that zenith. Okay. I'll show you this in a diagram. So here's the Earth. Imagine standing at the North Pole, and straight overhead is the North Celestial Pole, so Polaris would be there. Now, we're not at the North Pole. We could be anywhere since it's a virtual class, though most of us are in North Carolina, or at least somewhere in the Northern Hemisphere between the North Pole and the equator. So living down here, partway down towards the equator, the North Celestial Pole and Polaris will not appear at zenith, but where will they appear? And you can point to it. Again, north is this way in our class. Try and get it right. That way in our classroom. Yeah, you're doing it. It's right about there, part way up. Let me show you another diagram to explain that. So here we have the Earth, and here's someone standing in either North Africa or Southern Europe. But you can imagine spinning the Earth. That person would be in probably Florida, not too far from North Carolina. And here we've continued the rotation axis of the planet. And this it's hard to draw three-dimensional things on a two-dimensional diagram. This rotation axis is not between north and west. This is due north and due south, just up. So imagine taking this north-south line and then going up. That's where this is pointing. That's our rotation axis. And where it intersects the celestial sphere is the North Celestial Pole, and Polaris is very close to it. Down here's the South Celestial Pole. And zenith, again, is straight up. Now, looking at this, you can notice that there are collections of stars that either never rise or never set. And they're within these circles here. So stars will go around. From our point of view, the sky is moving. So stars will appear to move around the celestial poles. And this one here comes all the way down, barely touches the horizon, and comes back up. So that star and any one interior to it are always up, even during the day. We can't see them because the sky's too bright, but they're there. And then you have another collection of stars that we will never see. They're just in the southern sky, always. They're below our horizon, always. These stars we will see because they'll eventually rise in the east, come overhead, and set in the west. But these stars that we either always see or never see, we call them circumpolar stars. I'll write that out. And you can really see them nicely in time-lapse photos. So this was taken from some observatory in the Northern Hemisphere. They started taking this picture right after the sun went down, finished right right before the sun came up. And so you can see the stars moving on the sky, and you see there's a bullseye. That bullseye is the north celestial pole. When you go out and just look, you don't see it because you're seeing one instant in time. But with this time lapse, the geometry of it all becomes very clear. And you could probably point out Polaris. That's this relatively bright star close to the north celestial pole. It's not exactly at it, but it's pretty close and fairly bright given how close it is. And down here, this is not a little mini nuclear explosion or anything. That's a nearby city, and there were some faint lights. And if you expose for many, many hours, then it saturates, and that's what you're looking at there. You can see where all the cars drove in around the observatory, all their headlights were captured as well. Anyway, let me ask you a question. Looking at this, how many hours long was this exposure, was this photo? You could probably tell by looking at the star trails and how far they go.
8.
8, yep, very good guess. And that's what I came up with as well, because they go around once a day. And this looks to be about a third of a circle. So they image for a third of a day. A third of 24 hours is 8 hours. So this was probably 8 or maybe 9-hour exposure, which brings us back to our warm-up question, and we'll finish with that today. And this is where I ended up in the other section as well. So let me put that up for a second. So we had 42 answers, and I'll give you another 30 seconds or so to give it a try. But the question is, we watch a bright star move around the north celestial pole, in this case for 3 hours. Through how many degrees has it moved? And you should think of it really as a unit conversion question. But I'll shut up for just 15, 20 seconds in case anyone else wants to give it a go. Again, I encourage you to try these. No one knows if you get it wrong, so there's no embarrassment. And it's great practice for the homework and the exams. Consequence-free learning. Okay, well, we got, I pitched it. I got one more of you to answer. Another, okay. Another, good. Okay, so let's see what you all said. Show the values here. I see a lot of the correct answer. Show the histogram, and maybe I'll go here. So yeah, most of you got the right answer, 45 degrees. And let me just show you really quickly how to do that as our last activity. So again, you always start with what you know, which in this case was 3 hours, and I'm going to use the bracket notation that we talked about before. And you have to ask yourself, what is the relevant motion? It's the motion, the apparent motion of the sky around us. That's really just due to Earth spinning on its axis. And so something's given in hours, and we want the answer in degrees. So hours will go down here, degrees here. It's all about the Earth's motion, the Earth's rotation. The Earth spins on its axis one full circle, 360 degrees, every how many hours? 24, yep. So 360 degrees, 24 hours. It's really unit conversion. You have to think about the physical process. That gives us the conversion, but hours cancel with hours. That's way you put the numbers in there correctly. And
sorry, could you click on the tab again so it'll bring it forward?
That right there?
Yes.
So I'm just curious, when I'm like this, do you see half of the dot cam but not all of it?
Yeah.
Okay. Yep. So, and you put in a calculator and you come up with 45 degrees. Degrees will be the unit. And there's a question very similar to this in the homeworks. So you should be able to do that without any difficulty now. Okay, we're at 3:30, this is our ending time. So I'll stop there and I'll stick around and take any questions. Thanks for coming.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks for right here.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks.
Do you have a TA or a TA that does his office hours, or is it just your office hours?
It's just my office hours.
Okay.
And if you tried yesterday, I wasn't there. I mentioned it in class as a special case, but I will be there the rest of the time. I had an appointment
Awesome.
scheduled
Thank you.
before
Do we
they
have to make an appointment? Do we have
No,
to
you
make an
don't.
appointment?
You
Okay.
can come in and,
Awesome.
yep, and I'll be there.
Okay. Thank you.
I have a quick question to see if like this is like a correct way to do it or if this is like only one time it works. So I, instead of doing the unit conversion, I just did the Earth's rotation rate, the 15 degrees per hour times times 3.
Yep.
Does that work in all the occasions, or is this just like a one-time?
That works too. And
Okay.
that it is a unit conversion where you're using 15 degrees per hour as your conversion. Now here in the dot cam, 360 divided by 24 is 15. That's where that 15 degrees per hour comes from. So you can memorize the conversion rate. I did it this way because I like to tie it to the actual physical process. So it's not just like a mathematical thing you have to remember. Here, this is tying it to the geometry. What's actually moving? The Earth is. And we'll have other problems where we are talking about the Earth moving around the sun. And so the conversion there is 360 degrees in a year. This one is 360 degrees in a day.
Okay.
But
Okay, got you. All right, thank you so much.
I did it to where it was like arc minutes in 1 degree, like 1 degree equals arc minutes, like 60 arc minutes.
Okay.
Why? I don't know. I'm really confused. That's all.
So let me see exactly what I asked. So in this case, I asked through how many degrees has the star moved. So, so that's why it was 45. Now, if you want that in arc minutes, you can multiply it by 60. And whatever that is, let me see, 45 times 60.
No, I just like, so for 3 hours equals 60 times, no, hold on. Let me think this through.
Okay.
1 arc degree equals 60 arc minutes.
Yes.
Is that correct? Okay, so I just took 3 hours equals 3 arc minutes. I mean, 3 arc degrees. 3 degrees.
Okay. So I think I see what's going on here, and I understand the confusion, and a lot of people run into this. The units are similar, right? We talk about minutes of time and arc minutes of angle, seconds of time and arc seconds of angle. And the third counterpart is hours and degrees. But they are different things. If I say 3 hours, that does not correspond to 3 degrees. And
Okay.
yep. So you have to think about what's moving, through how many degrees does it move, over what period of time.
So what is an arc minute and an arc second? Like, where does that
Yes. So these
come
are
into
things
time?
that you're not as familiar with because, you know, you've had lots of problems before with length and mass and time, but not necessarily angle. Let me find my slides up here again and slide on back. So the sky, if we go completely around, is 360 degrees. And we divide that into 1 degree chunks. It's just our historic convention. And each of these, analogous to how you divide up a clock, 1 degree we decide corresponds to, I'm pointing my screen, let me use the cursor, 60 arc minutes. So you can see this 1 degree, you can break it into 60 pieces, and you can take one of those pieces and break that into 60 arc seconds. And just a way to divide angles into smaller and smaller units. They probably should have come up with better names.
Okay.
But they, you know, they're dividing into groups of 60 because we do the same thing with time and they're just mimicking that. But one is a time and one is an angle.
So arc seconds and arc minutes is just a smaller version of a degree.
That's right.
Okay. Thank you.
You can call them mini degrees and mini, mini degrees if you want.
Okay. Thank you.
Sure. Other questions?
So my question involves the ebook and the textbook and all that. So I ordered my textbook Monday from Amazon, the 8th edition, I think, and it's supposed to arrive today. But haven't had it. So I was under the impression that we could access the first part of it, or at least a small amount of it, from the ebook section on WebDesign. Is that wrong?
No, so
Okay.
but we're talking about these two things at the same time, so I can see how that got crisscrossed. So the textbook, Astronomy Today, different publisher, not connected to WebAssign at all. I just choose it because I like that textbook. The library offers a free copy of it, but since no one can enter the library right now, they scanned the first 3 chapters. I'm not exactly sure what the link is, but if you poke around and find it, you should be able to access those chapters, scanned versions from the UNC library.
My book should arrive today, so hopefully that will take care of that.
Yeah.
And as for the lab, I was trying to find the basically the textbook for the lab that came with the Skynet access card on Cengage itself, if that's the right website. I can't find it there.
It's not your fault. It should become available tomorrow.
Okay, perfect. Because I didn't really want to buy it marked up on the student store if I didn't have to. So.
Right. We did a major update of the curriculum over the summer, and the final updates are just being put in. And so I'll be setting these up closer to the last minute.
I'm excited for it for sure. So that should be a lot of fun.
Yeah, it should be a good experience.
All right, well, thank you so much.
My pleasure. Any final question?
Yes, sir. I got a question.
Okay.
All right. With the textbooks, like, do you recommend us to go ahead and get into like it's required to get the ebook textbook, like the $35
Yeah, you kind of need that one. That's how you're going to turn in the homeworks and many other things there.
So that on that helps us keep up with the readings and which ones we have for which classes, right? Like reading before each class.
Yeah, so the reading is in the Astronomy Today textbook. So there are 2 things. There's the Astronomy Today traditional textbook, and then there's the WebAssign that has the homeworks and supplementary notes. It has the reading assignment. Grades will be posted there, other things. It's a collection of all sorts of useful materials. And so you kind of need both, though with the Astronomy Today textbook, you can get it fairly inexpensively off of Amazon. If you go back to you don't have to get the 9th edition, which is what's in the bookstore. You could go all the way back to the 7th edition, and last I saw, you could get it for like $7.
Yep.
And then the WebAssign is $35. Now, if you buy from the bookstore, they mark up the price, but you can spend, if you have financial aid money, you can use that money. So if I were doing it, I would spend my fund money first, and then if I need to, I'd buy it off Amazon. But I would not pay for the 9th edition. It's too expensive.
Yes. Okay, I have one more question.
Sure.
All right. Like I was saying about the readings, like, are they like, is it like a document where it tells us like which certain readings to read before each class, or it's just like?
Yeah, not before each class. Here, I'll bring it up here. So here in the WebAssign ebook, they call it a book, but it's really a collection of notes. If I go under lesson 1, you can see I've broken it down into topics. And so you can go to each topic, and there's a reading assignment for different editions of the textbook, but they're all the same because the textbooks never change. So for that subsection, it says read chapter 1.1. And I normally will cover 2 to 3 of these subsections each time.
Oh, okay. So we need to read like 2 or 3 just to.
Yeah, 2 or 3 ahead.
Okay.
Or you can just bite the bullet and read all of chapter 1, and then you're good for a week or 2.
Gotcha. Yes, sir. Okay. That's all I had.
Okay.
All right. Thank you.
Thanks a lot.